Okay, we'll start the class. Okay, are you able to hear?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes,
Okay,
sir.
so today we are going to look at a new topic, that is some numerical methods for constraint optimization. So in the previous lectures we looked at Lagrange method. Okay, that is a manual method, and another is penalty function. Okay, penalty function is also a numerical method, but there you have to give, specify the penalty function, but in these methods you need not specify the penalties. Okay, it's more direct solution. Okay, so two type of methods are there. One is direct search methods. So this is based on direct logic or natural logic without the need of calculus. Okay, so this is somewhat similar to our grid search method. Okay, there is no calculus involved. So it is based on some sort of natural logic. Okay, that is, you make a grid, you start at one point and then you go to next point of the grid where objective function is value, objective function value is less, and so on and so forth. So no mathematics is involved in this, just human logic is involved. The next two, the next three methods are calculus based methods. Okay, that is sequential linear programming and sequential quadratic programming. So these two are in the syllabus. This augmented Lagrangian method is just for illustration. Okay, so first in today's class we look at these two methods. Okay, direct search method. So first we look at Lewis and Jacola's method. Okay, so what you see here is a feasible region, and these are the contours of the objective function, and the green dot is the actual optima. Okay, this green dot is the actual optima, and we'll try to reach this actual optima. So what is the method here? Okay, first the user has to specify a starting point x0. So x0 means actually x0 y0. Okay, it is just a abbreviated notation. The user has to specify starting point x0. Then the user has to define this window. Okay, whose sender is x0 y0. After that, after that the user has to specify a number of points inside the feasible region. Okay, inside the window. So all these points are randomly selected inside the window coordinates. You already know the size of the window and you already know the center coordinate of the window. So with a random number generator, you can select all these points inside the window. Okay. Okay, then we'll see what happens. Okay. A number of points are selected at random, centered around the starting point x0 inside the window. They are all checked for constraint violation. Constraint satisfaction. If any unfeasible point is there, they are replaced with a new feasible point within the window. So this is a unfeasible point. Okay, so you have to eliminate this point and you have to try again until you get the new point inside the feasible region. Okay, so that is the second step. And the best of these points is chosen as the starting point for the next iteration. And the window is successively narrowed. Okay, so here the contours of the objective function are coming like this. So the best point is this one. Okay, because this point is closest to the minimum. So this is the best point. Okay, because it has a smaller value of the objective function because it is close to the actual minimum. Okay, so you choose the best point. Okay, so this is your best point. Okay. Okay, so centered around this best point, you make a new window, and as the iterations increase, the size of the window becomes smaller and smaller. So centered around this best point, you fit a new window, and again you choose a number of random points around this around the center point, and again you choose the best point. Okay, so now this is the best point, and you make smaller window, and you go on like this. So finally, okay, so in the first iteration, all points were here. So all these points will migrate to this optima after dozens of iterations. Okay, so finally, the points will reach the constrained optima. So now, so let us look at outline of the method. The first you can specify number of iterations. Okay. So suppose it is 10. And the number of sampling points, say p equal to 3. So actually p equal to 3 is very small. You may need about 30-40 points actually to correctly find the optima. So just for illustration, we are using 3 points because it is easy to track 3 points in the lecture. Okay, first step is you select a starting point x0, y0 and specify a window size z, and centered around x0, find okay, we look at step 2 first. Okay, so this is the starting point x0, and you pick a window like this. Okay, and the user has to specify this length of the window. Okay, length of the window. It is a square window, z by z. Okay, okay, so that is the second step. So centered around x0, find 3 random points within the window. Okay, so within x0 plus or minus z by 2 and y0 plus or minus z by 2. Okay, so how do you generate a random point? You have to use the random number generator R. Okay, so the random x coordinate x is obtained by x0 plus Rx into Z, where Rx is a random number between plus 0.5 and minus 0.5. Then y is equal to y0 plus ry into Z. So ry is another random number between plus 0.5 and minus 0.5. Okay, so by generating the random number 3 times, you are able to successively get 3 points inside the window around x0, y0. Okay, so that is how you get x1, x2, and x3. So you have to generate the random number 3 times. Each time you get a random point inside the window. Okay. Okay, suppose this green point is the optima, and these are the contours of the objective function. Okay, so next step is, are x1, x2, x3 violating any constraints? If it is violating, then you have to replace it with a newly selected point inside the window. So suppose one of our point goes here, it must be rejected. Okay, must be rejected, and you have to try a new random number until you get a new point inside the feasible region. Okay. So that is an important step. Then find the best. Okay. Find the best of x1, x2, x3. That is giving minimum value of f of xy. So naturally, best point is this one. That is x3 is the best because it is closest to the contours of the objective function. Okay, so it will have this x3 will have minimum value of f of xy compared to x2. Okay, x2 is farthest. Okay, so x2 will have largest value of f of xy. X3 will have smallest value of f of xy. So this is the best point. Okay. Okay. So now this x3, which is the best point, becomes x0 for the next iteration. Okay. So so since x3 is the best, x3 becomes x0 for the next iteration. Okay, that is what is shown here. Okay, so now you have to fit a smaller window around this x0. Okay, so how do you reduce the size of the window? So the window is narrowed down using a window sizing factor called epsilon. Okay, so Z1 is equal to epsilon into Z. That is epsilon into the previous window size. Okay, so this epsilon can be like 0.5. Okay, so the new window size is half the previous window size. So the window size becomes successively smaller and smaller. Otherwise, the points will not converge. Okay, the points will be scattered everywhere. So you have to reduce the window size. Okay, so now choose another 3 points centered around the new x0. So these are the other 3 points centered around the new x0. Okay, x0. And again, okay, the contours are coming like this. This is the optima, and this is the best point. This is the next. Okay, this is the best point. Okay, and you have to make a smaller window around this best point and choose another 3 or 4 points around these things. Okay, so it will continue like that. So terminate using some criteria. Okay, one of the criteria is that there is no further improvement in the f of xy values between all the points. Okay, so as all the points approach the optima, as all the points cluster around the optima, their fx values will not have much variation. Okay, so you can specify a tolerance, and if all the f of xy values are within that tolerance, then you can stop it. Okay. Then the more the sampling point, say 10 or above, better is the solution. So if you have more sampling point, you can sample the feasible region more strictly, and you'll reach the optima much faster. So with 3 points, it won't converge fast. Okay. But 3 points are shown only because of the ease of representing in this lecture. So one example is there. Minimize f of xy because this large objective function subject to this inequality constraint and another inequality constraint, and xy is greater than or equal to 0. So if you want to solve this by Lagrange method or penalty function method, it will be very tedious. Okay, but in this method it is somewhat automatic. It will do everything by itself, provided you give the starting point inside the feasible region. Okay, so first choose x0, y0 by trial and error. Okay, so that x0, y0 should be inside the feasible region. So x0, y0 is chosen as 3, 3. And window size is taken as 6. Initially, the large window size. Okay, so in practice, how do you choose the window size? It depends on the xy range. Okay, okay, so the xy range is range is this much, you can take a window size, say, 1/10 of the range or something like that. Okay, so that is not mentioned here, but practically if you implement it, that is how you find the Z size. Okay, Z should be within the search range. Okay, so Z is equal to 6. Choose a large window initially. Epsilon equal to 0.75. That is the window size reduction factor. So after every iteration, window size will decrease by 0.75. And P is equal to 3 points. Okay. So in the first iteration, centered around 3, 3, find 3 random points. Okay. So this is 3, 3. This is a window. You have to find 3 random points, x1, x2, x3. Okay, so let us find x1, okay, or x1, y1. X1, y1 is obtained by generating a random number rx and another random number ry within the range of plus or minus 0.5. Okay, so MATLAB has selected rx equal to 0.018, ry is equal to minus 0.26. So you substitute it in this equation and you get the value of x1, y1 as 3.1 and 1.440. So this is 3.1, 1.440. Okay, x1 has been got. Next, you generate rx and ry one more time. Okay, then you get x2, y2. Okay, then you generate rx and ry one more time and you get x3, y3. So it is seen that x3, y3 will violate the constraint, at least one of the constraints. So you have to try a new random number. Okay, keep on trying with new random numbers until you get an x3 which is inside the feasible range. Okay, so now you got x1, y1, x2, y2, x3, y3 centered around x0. So that is the first step. Okay. So then among this x1, x2, x3, which is the best? It is found that x2 is the best because x2 gives the smallest f of xy value. Okay. So you have to understand that the computer program cannot see the objective function, contours and all these things. So it will find the best value of x by sampling the best value of x by finding the f of xy value. Okay. So the best is x2. So now x2 becomes the center point for the next iteration. X2 becomes x0 for the next window. So this is the center point for the new window. X0 equal to 2.754, 1.836. Okay, so okay, this is the new x0, and what is the window size now? Window size is 0.75 into previous window size. Now window size has decreased to 4.5. Okay, earlier it was 6, now it is 4.5. Okay, so now you have to find 3 points x1, x2, x3 surrounding this x0. Okay, 3 points surrounding this x0. So you have to generate a random number rx, ry 3 times. Okay, so let the 3 points are these things. Okay, so x1 is okay, yeah, x1 is this one, x2 is x2 is this one, and x3 is this one. Okay. Okay, so the search will continue like this. Okay, so out of this, maybe x1 is the best. Okay, and next window is here, and it will go like this. So the advantage of this method is that it will work by itself, and as long as it is a convex problem, okay, okay, then it will find the constrained optimum. Okay.
Sir, one query.
Oh.
Sir, the first point you are finding using Rx equal to 0.018 and Ry equal to minus 0.26.
No.
That is equal to 3.108 and 1.440. The second point, x2, y2, how was it found? 2.7454 and 1.836. How was that found actually?
Oh, this is the previous x2. Previous best value. This is the center point here.
It's basically another random Rx and Ry
Yeah,
values.
it was obtained in the previous.
Yeah, sir. So the Rx and Ry can be anything for anybody, right? So I can do it in a different way. The other person will do it in a different way. That like that only.
Yeah. That is how you do the.
Okay.
That is how you search the point. With 3 points, it won't work very well. So suppose you have 20 points. If you generate sufficient number of random numbers, you can search the feasible region very well. Okay. So Rx or Ry has to be generated 3 times. Okay, to get the 3 points. Okay. So what is the doubt you are asking? I'm not able to understand.
Getting the Rx and Ry is not so easy, right? That is the point.
It is obtained by MATLAB random number generator.
Okay.
Huh? If you make the function call for random number generator, each time it will return a new value of Rx and Ry. So you have to do it 3 times. Okay.
So the solution convergence for each and everybody will be different only then.
No. Finally, it will converge to the point. No, okay, because best point is selected the one which is closest to the minima. Initially, there will be variations. Okay.
Yes.
Initially, some people may have a good selection of random points, and another people may have bad selection of random points. But after some iterations, all these points will converge to the center of the contours. Okay.
Okay, sir. Clarify.
So because that the direction is fixed. Wait, I'll show you. So it will converge in this direction. Okay.
Okay.
All the points, see, any point which is close to this contour will be selected as best. Okay. Suppose you start with a particular population, your point is here. Another man start with a particular population. This point will be here, but all are pointing in the same direction. Okay. Okay. So finally, everybody will converge here. Okay. So that will work only if it is a convex problem. Okay. So suppose your feasible region is like this. Okay. Then objective function is touching 2 points here and here. Okay. Then it will be difficult. Convergence will be difficult.
Yeah. Thank you.
Okay. So this is one method which is based on pure basic logic without any mathematics. Okay, and another method is also there which is much more efficient than this. It is called complex search method. Okay, so it's an improvement over Lewis and Jacola method because the logic is somewhat better. It's a more powerful logic than the Lewis and Jacola method. Okay, so let us adopt this as the reference image. So this is the feasible region. Contours are coming like this, and our minima is here. Okay, our target is the blue point. So this you have to keep in mind. That is this particular direction of the contours. Okay. So Actually, the complex algorithm is very complicated to explain in the textbook. I have somehow simplified it using 4 points. Okay, with 4 points, it is easy to understand. So, so I am explaining this graphically, so it is easy to understand. Okay, so pick 4 points within the feasible region. Okay, that's x1, x2, x3, x4. More points, the better. Okay, so okay, pick 4 points in the feasible region. More points, the better. So suppose x4 goes out of the feasible range, bring it halfway to the center of gravity of the other 3 good points. Okay, I'm generating 4 points. 1, 2, 3, and 4. Okay, so this x4 has gone out of the feasible region. So what you do, you find center of gravity of this 3 good points, and you draw a line. You draw a line between this center of gravity and the x. Somebody is talking loudly. Stop it. Okay, so x4 has gone out of the feasible region. How to bring it inside the feasible region? So you find the center of gravity of the 3 good points, and you draw the line joining x4 and the center of gravity, and you move it halfway. Okay, halfway towards the center of gravity. Okay, so now the point has come inside the feasible region. So if it has not come inside the feasible region, again move it by another halfway like this. Okay, so you keep on moving this out of feasible region point midway to the center of gravity of the good points in successive attempts until it comes inside the feasible region. Okay, so how do you find center of gravity of the good points? The center of gravity of the good points is nothing but the average of xy coordinates of these 3 points. So that is also easy to calculate. Okay, so these are the equations used to calculate the midway point between x4 and x bar and between y4 and y bar. So the CG is x bar y bar. This is x4 y4. Okay. So this point is x4 apostrophe. So x4 apostrophe is equal to x4 plus half of x bar minus x4. Okay. So with these 2 equations, you can bring any points back to the feasible region. Okay, so now point 4, which was outside the feasible region, has been brought inside the feasible region. All 4 points are inside the feasible region. Okay, now pick worst of the 4 points. So worst of the 4 points means having the highest f of xy value. We are trying to minimize, so highest f of xy is the worst point. Okay, then this worst point is x2. Okay, so this okay, so as we noted earlier, contours of objective function are coming like this. So worst point is x2. Okay, because it is farthest from the minimum. Okay, so x2 is the worst. X2 is the worst point. So we replace x2 by x2 apostrophe, which is obtained by reflecting x2 through the center of gravity of the 3 good points. So this is the 3 good points who are close to the minima. Close to the minima, you have to find the center of gravity of the 3 good points, and this bad point x2 has to be reflected in the opposite direction. Okay, through the center of gravity. Okay, so what is the meaning of reflection. So suppose you're standing in front of a mirror, when you're standing like this, then mirror image will be obtained at an equal distance behind the mirror. Okay, so in the same manner, this point x2 is reflected equal distance behind the mirror. Okay, so it is going in the good direction. Okay, because the contours are starting from here, it is being reflected in the good direction. Okay. Okay. So why is it reflected in the good direction? Because it is being reflected through the center of gravity of the good points. Okay, so the direction is right. Okay, so in this particular case, when we reflected x2, this x2 apostrophe is going out of the feasible region. Okay, so what to do now? Okay, so now it has gone out of the feasible region due to reflection. Okay, so what you have to do is that using the method mentioned in the previous slide, it has to be brought back to the center of gravity halfway. Okay, I already showed you the formula for bringing a point halfway to the center of gravity. So that formula can be used to bring it halfway to the center of gravity, and you have to keep on repeating it until this point x2 apostrophe comes inside feasible region. Okay, so this is the final set of points in the second iteration: x1, x2, x3, x4. Okay. Okay, so next. Okay, some equations are also given here. Equation for reflecting a point x2 about x bar y bar. Okay, so this point is x bar y bar. This is the point x2, and this is the point x2 apostrophe. Okay, so if you have equal reflection means the distance before the mirror is equal to distance after the mirror. So x2 apostrophe is equal to x bar plus x bar minus x2. Okay. So you can also have unequal reflection in this algorithm. Okay, by varying this parameter alpha. When alpha is equal to 1, you have equal reflection, and if alpha is less than 1, then it will be reflected less. Okay, so if alpha is less than 1, the distance after the mirror will be less than the distance before the mirror. So the user can control the reflection distance. So sometimes if you give lower value of alpha, the risk of the point going out of feasible region is reduced. Okay. 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 So if the reflected point is out of the feasible range, bring it back halfway to the center of gravity of the other 3 points. So the procedure is continued by replacing the worst of the above 4 points with its reflection. Okay, so this is the new generation. Okay, so let us see what is the worst point. So as I said, contours are coming like this. Okay. Okay, now x4 is the worst point. x4 is the worst point in this current iteration. Okay, and this is the 3 good points. This may be the center of gravity. So x4 has to be reflected like this. Okay, x4 has to be reflected. X4 apostrophe will come here, and then you now say you bring it halfway like this. Okay, so x4 will come here. X4 apostrophe will finally come here. So for the next generation, point will be this, and this, and contours are coming like this. So you can see that initially all these points were somewhere here, and now all these points are approaching this optimal point. So if you repeat this a sufficient number of times, you will reach this optima. Okay, but actually you need to have 10 or 20 points, okay, so that the search space, feasible region can be sampled more accurately. Okay, the program terminates when the differences between differences between the center of gravity of the points and the individual values of the f of xy's become negligible. Okay, so initially all the points will be scattered like this, okay? Scattered like this, and so in the end, all will be clustered like this, okay? So you can find the x bar, y bar, then f of x bar, y bar, and the individual f of xy values of all these points must be close to this f of x bar, y bar. That is within a tolerance limit. At that point, you can stop. So you can specify a fine tolerance limit like 0.001, etc. So finally, all these points will come very close to each other at the optimum. Okay. Okay, so we can stop here. So these are the two good methods of finding the constraint optima without any headaches of using penalty functions or Lagrange multiplier or anything like that. And they work for simple problems with only one specific optima, or it will work for convex problems. So you can stop here.